Welcome back to Revise and Resubmit, the podcast that takes, those really dense academic papers and makes them surprisingly interesting. I'm Pavlov.
And I'm Nikita. Happy holidays, everyone. Today we are looking at the very near future of medicine, a future where you might not need a surgeon's scalpel at all.
That's right. I mean, we're talking about getting rid of invasive neurosurgery for certain things.
Yeah.
Completely.
Which is a huge deal. Traditionally, if you want to implant bioelectronics in the brain, it's a major, major operation.
Oh, incredibly risky. And that risk is a massive hurdle. It's what this new work is all about clearing.
So we're discussing a technology called Circulatronics. We actually touched on it before in our look at the Nature Biotech paper.
But of course, the link to that is in the show notes. But for this holiday special, we're doing something, well, a little different.
We're going straight to the source.
Yeah, we've handed the microphone over to our producer, Mayukh Mukhopadhyay. He recently spoke with the paper's first author, Dr. Shubham Yadav.
Dr. Yadav's background is just incredible. A PhD from the MIT Media Lab, now a postdoctoral fellow at ETH Zurich.
And Mayukh asked him the big question. How on earth did you teach electronics to deliver themselves? Let's join them.
Hello, everyone. And hi, Shubham. Welcome to my podcast.
Hello.
It's Revise and Resubmit the Mayukh Show. And we will start right away. Okay. So thanks for joining in. So we will.
Thank you so much.
Thanks. So, I went through your PhD topic and like you defended it a few weeks ago, I assume. And that sounds like very much science fiction. So when you explain it to someone in your family gathering, so what do you say about it?
I'm like, it's an interesting way. So I take it in a slightly different way, actually.
Yeah.
So I'm like, I'll give you a different perspective on it. So
Sure.
imagine I'm like, currently we talk about a lot of microplastics, right? I'm like, where we talk about a lot of pollution, especially I'm like coming from India, we talk about like the air quality in especially in Delhi. I'm like, I come from like a small city like near Agra. So I'm like, so the thing is, when it comes to environment, the pollution is really bad. And then there's a lot of things where we talk about we are inhaling like the same, like say the environment there, and then it has a lot of microplastics, a lot of like dust particles which are there. So the world is concerned about not having microplastics inside the body. So that's where I want to relate things to. So the thing is, I'm like the work, like the PhD research I did, the paper you would have seen, you would have read about, it's basically about, I'm like, specifically that work, it's about how do we implant microplastics inside the body in a non-surgical, in an autonomous manner. So I'm like, the thing comes from this perspective is like, we make these electronics which are organic photovoltaic devices. When we talk about organics, it's basically plastic. And like that's what my work has been about, developing microplastics which can cure you and which can be used for therapeutics, which can be used for like early disease detection, and then we can implant it anywhere in the body. So the idea is we leverage the microplastic the world is afraid about. We use it to cure diseases. We use it to find out what is wrong with the human body. So it's just a different perspective of looking at it. So I'm like, when I talk to my, like say, parents, like my partner, maybe like my family, extended family, relatives, I just start with this kind of a thing, that what I do is I just implant microplastics in the body, and then but we make sure that it helps you, not like say really affects you in a negative way. So I'm like, it's a slightly different take which people find it amusing, but it's a good starter to talk about.
That's interesting. Like it's the good side of microplastic you are trying to exploit it.
Of course.
Okay.
Yeah.
So
And like, that's the way we put it. Yeah.
great. That's a new perspective to learn. So like it's a follow up here. The question is like,
Yeah.
if you had to describe your PhD in say one analogy in to a very non-science from a non-science background
Mhm.
relative or a very
Mhm.
kid,
Yeah.
so that they can really remember the study. So
Yeah.
what
Uh-huh.
would it be
Yeah.
like?
Yeah. I'm like, so one way we can put the work, like if it's like say defining it in a sentence or something like that, it's like if you have a disease anywhere in the body, we will detect it, we will cure it, and we will do it in the most minimally invasive manner
Mhm.
so that you do not feel pain, you do not even, I mean, the thing is, we'll detect it at such an early stage that you will not even know that there is a problem which is imbibing or which is getting created there. So the idea is we do everything in a really minimally invasive at such a really early stage that we want to make sure that the humans can have like can live their life to the fullest, and then they can live a more like a disease free life at the end of the day. So I'm like, that's the all the PhD work has been about. I'm like, and then it's just not about that. I'm like, it's just some part we're getting started. So I'm like, it's just the initial results we are able to share with the with the community, and then the idea is to we are still working on many different aspects of the work to take it to the translational side of the work, and then make sure that we can actually reach that stage where we make sure that you do not need a brain surgery, or in theory you do not need a surgery. All you need is a vaccine. All you need is a single injection which can help you cure an array of diseases. Yeah.
Got it, got it. I mean, yeah, I mean,
Mhm.
that's truly novel. Like, but what I understand, like this paper, I can understand it's the tip of the iceberg, but
Of
the
course. Yeah.
entire ice was your PhD journey. I mean, I
Mhm.
understand because I
Yeah.
mean, from personal experience, also, it's not very straightforward. So,
No, 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 no.
so I mean, during this long PhD journey, to keep your
Yeah.
sanity
Yeah.
intact, like what was the one non academic habit or hobby that you quietly kept on doing that help you motivated to
Mhm.
do your work in a more concentrated manner and
Mhm.
keep you more productive?
Yeah. No, fair enough. Yeah. I'm like, yeah, of course, I'm like, the PhD, it was not an easy journey. And like, the thing is, the journey of if you are a scientist, if you do research, everyone knows that I'm like, you're living a life of failures every day. I'm like, nothing works. I'm like, that's the summary of 6 years for me. I'm like this. I'm like technically 4 years for my PhD, where every day nothing works. If something works, then the next day again things do not work because something works. Then you move on to the next part, and then you keep on repeating this every day. So that's how it is. But then the thing is, I'm like, you are there for this kind of a life for a different reason. And the thing is, the motivation is always about that you are doing something which will have a meaning, or which will be more impact, like which will have some impact on the human life at the end of the day. So I mean that's the bigger motivation, but and the motivation can only keep you moving or going towards something for a certain short amount of period. But the thing is the daily activities or the daily habits which are more important. So I'm like, for me it was literally like say, I'm like, the nice thing about MIT is I'm like, it's right next to a river. I'm like, we call it like it's a Charles River. So it's nice. It's a good place. And then I'm like, they make it nice for walks and things. So I'm like, it was like basically just going on random walks along the Charles. And that used to be the constant pace, which I know that everything goes wrong, but that will not go wrong because I'm not doing anything like with like the really consistent pace throughout, where I'm like just creating some habits which you like, and then which you can go back to again and again every other day for years, like not just months, for years, and then that keeps you going. And then I'm like, of course, I'm like, I had my own side things to like say. I'm like, cooking is something which I really learned after moving to US. So I love cooking. So I'm like experimenting with food. I'm like,
Okay.
the good thing is anything comes out. It's as long as edible, it's a good experiment. So it's minimizing failures in some part of my life. So which is not controllable. So that's the a few things which kept me going. And then I'm like, it's still keep me going now. So I'm like, it's just the way of life now. Yeah.
So to summarize, it's a daily walking and doing the daily chores and cooking. So cooking has been
Yes,
therapeutic for
I'm
you.
like, yes, oh, definitely. Yeah. I'm like, that's the part and parcel of it where I'm like, just minimizing risk in other forms of the things and then keeping things nice.
So our the theme of the podcast or the title of our podcast is revise and resubmit. So I understand you might
Mm-hmm.
have received so many RNRs in your journey.
Oh, wow.
So
I'll,
cooking and walking
yes,
is something that kept you sane while going through that RNR journey.
definitely.
Okay.
Yeah. Oh, wow. Those were like, it was tough. I'm like, I've had really tough R&Rs. But yeah, I'm like, you need something to keep you going. And then, yeah.
Exactly, exactly. Thanks for that
Mm-hmm.
insight. Yeah, this will really help. I mean, newcomers who are into PhD. I mean, it's not a bed of roses. Yeah.
No, no, fair enough. Yeah.
So, I mean, now we will go back a little.
Mm-hmm.
Like, I
Okay.
mean, I
Uh-huh.
will let us take this back to our to the school level because we have your journey
Mm-hmm.
to the like.
Mm-hmm.
So, when did you first feel the pull towards electronics and physics rather than medicine or pure math?
Mm-hmm. I'm like, it's like, I don't really know the pinpoints about it, but I'm like, growing up as a kid, I'm like, always liked math and then physics on top of it. So I'm like, it was never about electrical engineering, let's say. It was more like, say, maths and physics. I'm like, at some point of time, I'm like, it's the classic Indian academia, right? And that's where you have to make a choice of whether you want to, like, maybe I'm like, if you are looking for like some like degrees like engineering or MBBS and like a more professional degrees, you end up taking a decision whether you want to pursue either of the fields. And like some people do both, but like I was not that keen into biology. So at that time it was more about, okay, I want to pursue something in physics. So that's why I ended up like to opting for like say those classic science based like engineering based courses and then preparing for JE and everything. So it all went in that direction. But I'm like, it was I'll say like even like say my engineering work, I'm like the kind of courses I was taking, it was most I'm like it was more closer to physics rather than electrical engineering. I'm like like most of my undergrad was about semiconductor device physics, which is like you're trying to understand, like say, the physics of how a single device, like a semiconducting device, works. Be it a PN junction, be it a photovoltaic device, be it something else like some MOS-based technology. So it was always about that. But then I'm like growing up, I'm like at some point of time, I'm like I was finding it interesting, but I'm like, it was mostly the shift happened during my like it's when I started my masters at MIT, where I was getting more and more curious about biology or like say looking into like this specifically like nowadays I can call it like say neurotechnology. But at that time I was too naive. So at that time I was like more interested in okay, I've worked or learned a lot about devices, but how about we look into the application side of it, being an engineer? So that's where I'm like neuroscience or like say working with biology and cells. That's where the curiosity led me to working in this kind of a field where I'm like developing new kinds of neurotechnologies and then thinking about different applications, but with a mindset of an electrical engineering or a applied physicist. So yeah.
Great, great. I mean, what I understand is from your profiles, I got that. I mean, at IIT Kanpur, where you did your bachelor's and higher studies, like you were working on organic solar cells. So, any teaching from that also did it help in your projects or in PhD, or in PhD it was entirely new ground?
No, no. I'm like the thing is for as part of my like say like during my undergrad, I'm like I did a thesis there as well, which was about like say improving like organic photovoltaic devices, like their
Okay.
efficiencies. And then the idea was we'll not like say modify the processes, but I'm gonna use the established processes and then introduce one additional layer of material which can lead to better performance of those devices. So I'm like, it was directly, it really helped, like say, directly translating that mindset as well as like say the technologies. Because I'm like there, I'm like I worked, I'm like I like published a couple of papers there as well from my undergrad. But I'm like we were using similar devices, but then they were like more meant for the solar cell or like the photovoltaic community, making things from like the perspective of that you are harnessing the solar like energy which is out there in a more efficient way. But then here it was more about okay, can we use the same technology, miniaturize the devices, make into something like this really efficient on a subcellular scale. So the core technology was still like came from like the direct expertise of working on those kind of devices. And then I was looking from a different perspective, or like say having the different constraints or the engineering design rules that okay, if we want to make circulatronics work, how do we make it work, and then what kind of constraints we have. So that's where I'm like the organic solar cell really thrived in all those under all those conditions, be it efficiency, be it flexibility, be it the ultra miniaturization of the technology. So I'm like all of those things went directly into making this a reality. So that's where I'm like, and like pretty much I started like say, I think right after COVID, because I'm like I joined before COVID, and then
Okay.
after COVID, then I was just like okay, let's start making this a realization, and then how do you go about building this specific technology for making the bigger platform of like circulatronics function and like make it work. Yeah.
Got it, got it. So, I mean, I'm curious
Mhm,
because what happens is, even my batchmates and all, they even if they come from electronics or electrical, because I am from the electronics and communication background. So most of them
mhm,
shift towards the data structure and algorithm part and competitive programming, and they switch on to the FANG companies. Like
mhm. Yeah.
my question curiously is like, was it a natural progression for you, or it was a very very cognitive switch you did, like I want to pursue this
Mhm,
into deep research, and rather than not too much think about the FANG and or the
yeah.
investment banking part. I mean, this is
Mhm,
something,
mhm.
a moral dilemma that all the people
No.
that's fit. So what was your thought
Yeah.
process? I mean,
Mhm,
any trigger or any
mhm,
professor told like you should go to research, or other, like what happened that switched that I would go to research? Maybe you did a few years in industry but you switch again back. I mean, this is
mhm.
a very tough choice to make when you have
No,
a,
no, fair.
so I mean, I
No,
want
no,
to know
no,
your
fair
thought
enough.
process here.
Yes. Yeah, yeah, no, no, fair enough. So I'm like, the idea was, I'm like, the thing is, growing up as a kid, I always find research to be fascinating. It was just like I did not know what exactly research is. I'm like, I come from a family background where I'm like, I don't know any researchers or like anyone having a PhD or like a master, like even like a postgraduate degree. So it's like like coming from that kind of a background, it's like you do not get a lot of support from mentors and advisors as such. I'm like, unless you find some. But I'm like, I always had this idea of okay, I want to do research, but what exactly research is, doing it as a profession, or like doing it like from like say day to day. I'm like I really know like really limited ideas of it. But I'm like that's where I feel like IIT Kanpur was really instrumental in providing the support. I'm like I started working with professors there from my second year. I'm like from my like sophomore year where I'm like usually like people are like start to prepare for like the internships like from second years, third years they want to go out and then maybe get a foreign like a US or like an international internship, maybe do some research, then they start to apply for like all the like say fancy nice companies. But when it comes to the placements, so I'm like everything was there. I'm like of course I'm like all the distractions or the so-called facilities, I'll put it that way. I'm like everything was there, all the support was there, but I'm like I was always curious about how the research in general is done, and then what's the was the way it works. So I'm like, I was working with the professor there during the second year, third year. I'm like, when it came to the fourth year, I was still not really sure. So that's where I'm like, I converted my undergrad degree into an integrated bachelor's and the master, so that I get to spend more time doing research and then understand more about it. I'm like, my advisor there, I'm like, he was really nice, really kind and helpful. I'm like, he really supported. Like, I learned a lot from him, like how to do research in general. And then I'm like, he's probably that was the first time I'm like, I published my first paper with him. Like, went to some conferences. I'm like, understood the structure behind it or how the system works. I'm like, even after that, I was not sure. I'm like, the thing is whether this is the kind of life I want. That's where I'm like, I joined Intel and then worked there for a year. And then at some point of time, like while I was working there, I realized, okay, probably this is something which I'm like, maybe research is something I'll prefer to do more. And then that's where the switch happened. And I'm like, okay, I really want to, let's say, go for a PhD, understand, and then do it in give research more time, because I'm like, sometimes to do good research, you need time. I'm like, it's as simple as that. I'm like, it takes years and years to do something which is meaningful and which is something which feels you feel satisfied with. So that's where I'm like, I like applied for PhD programs, and then I started my PhD at MIT there. And then I'm like, yeah, I just defended like a couple of months ago. And then now I'm like, I started my postdoc in, let's say, Zurich. I'm like at Institute of Neuroinformatics. So I'm like, I'm liking this phase as well. So I'm like, it's too early for me at the moment, but I'm like, it's been nice. Where I'm like, I'm still liking this life of a researcher, doing it more as a profession. So I'm like, we'll see. But yeah, I'm like, it's been something more like a self discovery to understand that if I want to do this, how do I go about it, and then what is the like say the infrastructure around it, what the day-to-day life looks like. So I'm like understanding the profession, or like understanding how the system works as well. So I'm like, it's been take some time, but I'm at the moment quite liking it.
Got it, got it. We will take a bit notch back, and we will go into the industry experience part also, because we want. Basically I want to understand, like, you were there as a SOC design engineering role. So
Mhm,
what part of that job you think is now
mhm,
helping you in this
mhm.
research area? So if you
Yeah, no, I'm yes, no, I'm like, so the nice thing is, I'm like, it was a short stint. I'm like, I stayed at Intel for a year, but
okay.
it had really, I'm like, it helped me in a couple of things. I'm like, the first thing was, I'm like, I made a lot of good friends in that was short 1 year period of time. I'm like, I'm still in contact with a bunch of people from that time. But one of the things which is like really like which I think academia is still not at par with is collaborations. And the thing is, when you are working at, I'm like, my job was like as a associate design engineer. I'm like, if you want to make a SOC, it's not just one block. I'm like, it's a lot of connected blocks which you are have to like everything needs to work in tune. It needs to be connected well. Everything needs a lot of things in the background. So you cannot pull all of those kind of things just by yourself. So I mean, you need to rely on 100 other people. Everyone has their own well-defined roles. Everyone is working parallelly, making sure they deliver in time, because I'm like, there is a time, like a deadline associated with whatever you are doing. And that's the part where I feel like doing things as a profession, you have to act like a professional as well. So I'm like, I think so this collaborative effort, knowing or owning what you are responsible for and working like in sync. I'm like, it's something which I don't really see happens a lot in academia in general. But I mean, that's something which I really learned from my like say stint at Intel. So and then it is something is it still helps me a lot when I'm like collaborating with people, working on different complex projects. Then it's always nice to work in teams rather than just working or making everything work on your own. So I'm like, it just really helps.
Got it, got it, got it. So, I mean, is there any concrete example you want to share, like that
Mhm.
you had learned in Intel and that really helped you here in doing the experiments or the complex bioelectronic structure? Was there any?
Oh,
I mean,
no, definitely. Yeah, yeah, yeah. No, so the thing is, I'm like, when I was developing this technology, I'm like, there are like a few components to it. So one of them, I'm like, the way this works is, I'm like, you develop the electronics first, then you have to like create these hybrids, which is a lot of in vitro work, and then finally you work with animals where you are doing a lot of in vivo validation. So I'm like, it has these different structures and components of electronics, which is all like the nanofabrication, like they're using certain specialized tools for it. And there's a lot of in vitro work and there's a lot of in vivo work. So unlike it has a lot of like you need different skill sets for like pulling off all these different complexities of things. And then I'm like, that's where I'm like, I had like the friends in the lab who like one was a neuroscientist who helped me tremendously with the in vivo experimentations, not just design but collecting data, analyzing results. Then there were like say a chemist in the lab who helped a lot with like say the surface chemistry or like the functionalization things, and then doing some in vitro experiments. Then there was another guy, and like he's also from like he's like 3 years junior to me. I'm like he joined like the lab 3 years, but he's also like from IIT Kanpur. I'm like an undergrad from there. So I'm like we got get along really well, and like he helped me a lot on the device, like say like the nanofabrication side. So it was basically getting help from different people with different expertise while keeping everything in sync towards one big goal of okay, how do we make this technology function or work? So collaborations and then let's say just communication on this, because sometimes I'm like just sharing what you exactly want can be not so trivial in some cases. But I'm like just sharing that, okay, this is the goal, this is the vision, this is what we need to do. And then once we do it, the next thing will happen this way. And then I'm like, all the work, I'm like, if you look at the paper, I'm like, we talk about timelines where I'm like, there's a certain timeline associated with it. And then some of the events need to happen by hour by hour. So if you miss even an hour here and there, the rest of the process you just cannot go through. So you have to make sure things work in time, in sync with everything. And then that's where I feel like coordinations, collaborations, sharing what exactly you need. So I'm like, all of that thing comes from like all these different experiences, especially I'm like working at Intel, I'm like working in teams there. I'm like, we used to work with, I'm like, at least, I don't know, there were 5 or 6 different teams. We are like coordinating actively, making sure that one person gets their things done, then we have to really talk to the next team, get things done. Sometimes there used to be a back and forth as well. So on the getting all the coordination, it takes some time to get used to that. So yeah.
so I mean, if we look back, like if we had gone
Mhm.
from straight IIT Kanpur to direct MIT academia rather than having the Intel
Mhm.
part, you
Mhm.
think it would have been a different trajectory or different way of approaching the project, or Intel really helped to, I mean, somewhere here?
No, yeah. No, I mean, the thing is, sometimes you need all of these things to, like, the thing is, there's no way without collaboration, without working with people, you can make this work.
Yeah.
So the thing is, if you have the skills, then it's a easier transition or a smoother transition. But if you do not go through these kind of learning, then you have to learn this. So and the thing is, sometimes everything converges towards that final, nice, elegant solution. So the paths can be different, but the final thing needs to be that way. So it's just like it's more about if I wouldn't have gone to like say Intel or maybe if not IIT Kanpur, if it was some other IIT, the paths would have been a bit different. And like what kind of things would have, and I think is when you need these skills, you would have needed to learn it at some point of time. I'm like, then those periods would have changed, but otherwise, I still believe it would lead to the same conclusion that okay, you need to have these skills or you have to work with people, and how do you make that work. And like sometimes it's just like you will learn it with like not so good experiences, but otherwise sometimes it can be really smooth. So it's just a matter of like how do you learn, when do you
True, true. Thanks.
learn.
Like,
Yeah. Hmm.
so
Hmm.
this the next few questions are very much targeted to like a younger self of you who is still in Intel but want he's in a very comfortable zone in a industry but want to switch to academia. So the
Hmm.
question here is like about the media MIT Media Labs. Like it was
Hmm.
something in the backside of your head that I will be targeting it this, or it was a natural choice came to you, or you already planned for other schools as well. Like I mean, what was the moment like where I want to go
Hmm.
back to school and want to work on nano electronics and brain? So how that thought
Okay.
process came, and when what did you apply other than MIT, or you wanted to go very pinpointed to this lab only?
No,
When you
so
go,
yeah, no. I think so. The thing is, I'm like, it was never about MIT or MIT Media Lab ever. I'm like, the thing is, I'm like, when you're applying, it's like you want, I'm like, the clarity in the head was more about, okay, I want to do PhD and then do some research. It was going to be about devices and its applications. I'm like, that's the broader idea I had in mind. I'm like, and then I'm like, when I was applying, I'm like, there were many other like universities. I'm like, I applied to quite a few, probably close to, I don't know, maybe 8 or 10. I'm like, I don't remember exactly, but like quite a bunch of. And then it was always like, say, some places it was like say, about like say developing devices for AI computation. I'm like, could have been a really different path. I'm like, especially given now like the amount of like attention AI and devices is getting, could have been an interesting path as well. So, but the thing is, I'm like, it was like some places I was applying for like say more scalable solutions for like say renewable like say means of energies. I'm like,
oh,
be it through photovoltaic or like the piezoelectric. I'm like, there's a lot of scope out there as well. So I'm like, either looking, I'm like, it was the core idea was okay, there will be nanoelectronics or there's semiconductor devices, and now which kind of areas like the application it can lead to. I'm like, be it environment, be it AI or computation, or be it biology. I'm like, biology was something I was not really focusing at that time. I think it was just like my PI. I'm like, I think she was starting a new lab, and then the project sounded interest. So that's where I applied. But otherwise, it was, and the other part, I'm like, was never about schools either, honestly. It was about specific labs
labs.
which are doing interesting work. So I'm like, especially I'm like, if you're doing like applying for PhDs or starting a PhD, I'm like, the focus should be on the lab rather than anything else. I mean, whether you like the kind of work or the research direction the lab is going, then you like if it aligns well, then that's the way to go about it. So yeah, I'm like,
So like now, I mean, from
mhm,
coming from IIT and Intel, from India specifically to a new culture in the MIT Media Labs, from professional, from academic, from a cultural way, like what surprised you the most in the research culture? And I mean,
mhm,
what problems did you face to adapt to this culture, or did you find this very comfortable,
yeah.
or you had any challenges to also?
So, no, I think it was never easy. And that's the first thing. I'm like doing anything new or like something which you are not really like feel at home with, it's always challenging. And I'm like, it was definitely challenging. I'm like, we had some other logistical challenges, but I'm like, all the conceptual and the research related things were of course there. But I'm like, it was like, say, I'm like, I was like, say, the first student in the lab, and then the lab literally started from 2019, like the fall semester. So I'm like, we did not even have lab space.
Okay.
So I'm like, we had to really build, like, get access to lab space, build equipments. And like, if I want to do an experiment, like the way to go about was that okay, we get that equipment, like either you buy it or you build it, and then you do your experiment. So it was always like say the most, like say you have to, I'm like takes a lot of time and effort where you have to build equipment, setups, and then collect data rather than things which are already established and set up there. So it was a different kind of an experience from that perspective. But then I'm like the other thing is I'm like that's the nice part of doing something like this. So I'm like as an engineer, once you do it, then you can do it again and again for anything else. And then as a researcher, it helps a lot because once let's say like we talk about from switching from electrical engineering to neuroscience, it's a big switch, but then the basic approach still remains the same where I'm like, okay, your next experiment needs something like this. Let's read about this experiment. Let's understand what it takes, what is the way to do it. Then you go get all the resources needed for it, understand what is the standard practice to do those, to conduct those specific experiments, and then you do those experiments. So it's like become, I'm like it's like once you start breaking it down into the next step or the final step, it becomes like a pretty similar approach in anything we do in life in general as well. And like even let's say if you are, I don't know, maybe let's say Intel, and like if you are working as an associate design engineer, you're like, okay, all you have to do is like reach out to the person, let's talk to them, what are the problems they are facing, let's debug it. Either you can debug it, if you can't, you find another person who will help you debug that thing. Then you go back again, sit back together, solve it. If you cannot solve it, then you find someone else who can help you. If you can solve it, you move to the next stakeholder, get them on board, see that thing works or not, and then you keep on building slowly and move towards the big idea that okay, we have to deliver this project within this time frame, and we deliver it. So the same approach is just like a slightly different context. But then I'm like, it's like once you get used to it, then it becomes sounds easier. That is not like oh you have to do it again. It's just like okay, the same process, just some big key element changes, and then everything else remains the same. So there is, I'm like one nice way to say it, there is still order in chaos. So something like that.
Got it. Got
Yeah.
it. So now we will move more towards the, I mean, joining Dr. Sarkar's lab. She's also from
Mhm.
the IIT background, and she made a big after UCSB, and she made a lab from
Mhm.
scratch there. I mean, that's I mean very
Mhm.
commendable thing to, and working for her. It so
Mhm.
like so when you first encounter Professor Sarkar's vision for this
Mhm.
non-surgical brain implant, I was also reading in one of her LinkedIn comment, like she faced more than 35 rejections for the funding for this particular because no one wanted to believe that this could actually happen. And so I wonder like what clicked in you personally, and how you
Mhm.
found that this is convincing and this can be done. Like what was the, I
No,
mean, supervisor and student chemistry between you both, like it
yeah,
sounds convincing.
no, yeah, no. And the thing is, I'm like the nice thing is, I'm like both of us have a that engineering or like a, that applied physicist like mindset or the approach to do things. So the thing is, I'm like when she had pitched this idea, okay, it was more like okay, we will, how can we like say do surgery-free bioelectronic implants? It sounded really like no, like say it does sound like it's science fiction, but then we really discuss for like say it's not like a discussion for a day or two. I mean we are just continuously discussing for months and months where we are like okay, if it's possible, how do we go about it? I'm like what are the things we need to make sure that this can work? Because I'm like I was planning to do my PhD dissertation on something like this, so it has to make sense in to someone at least. So that's where I'm like, we really went down to the basics. It was all about looking at just numbers. That okay, if we take electronic device for example, I mean the idea was of this idea of creating these hybrids was there. Where I'm like, there have been some literature which exists out there where instead of electronic, where people have shown drug delivery, people have shown like say like I think there's like one like professor at Harvard, and he's also co-author of the of this paper. unlike Samir Mitragoth, and like he has shown a lot of interesting results of cell-based drug deliveries. So where we are like, okay, this sounds interesting. That's where I'm like, the initial idea start from. That okay, people have shown something like this, and then coming from an electronics background, both of us were like, okay, how about we, like say have some like implantation or targeting like of electronics from this perspective or from this kind of a method. That's where I'm like, we really like most of our discussions used to be about electronics rather than the cells or how do we do it, because I'm like there were always someone, and there's a lot of literature out there, we're like, okay, this will work, it's just a matter of how do we make sure the electronics is still working. And then I'm like, we had a lot of discussions and like well, different opinions, a lot of arguments, of course, because without that, there's no good science. That's where I'm like, and then I'm like, we went to the brute numbers, pure numbers, and then photovoltaic made every sense. And that's where I'm like, I was like, thing is, I had all the background, I needed to pull this kind of a thing. And then photovoltaic was still making the most sense at that time. We're like, okay, how about we just develop a photovoltaic technology and then we show something like this. So I'm like, it was like, say, and like initially, sometimes it sounds like to an outsider that, okay, it might be really unrealistic, but when you really break it down to the basics, to the most basic numbers, if things still make sense, then yes, it's no longer science fiction. You can just really make things work. And then yeah, I'm like, of course, I'm like, we were applying for a lot of grants, and like, it was not a nice situation for a few years. I'm like, it was really difficult. Where I'm like we were collecting data, but I'm like, still the data was really promising. Where it really, I'm like, to convince scientists, it's not easy because you need a lot of data to show that this is possible. So on the to reach that stage where we had the data we wanted to show, it can convince other researchers. It took us a lot of time. So that's where I'm like she was writing a lot of grants. We were writing things. We were submitting to I don't know how many places, but then they were just not going to just for this period. And then once we had all the nice results we wanted to show, and then it was easier because I'm like, once you show these kind of results, because of like publication, it took 2 years to get it through the review system. But so the idea was, I'm like, we always had the results 2 years ago as well. So that's where we started to apply for grants, for funding, and then that was easier because now we can convince people that this kind of an approach, this kind of a technology does make sense. So yeah, I'm like, it's a like I'll not say it's a standard process, but it's something which is like it's a process of its own where you have to like go through like a lot of rejections. Of course, I'm like, it's not easy. I'm like, it's really bad. Like it's like not bad. I'm like, it's difficult, and then you have to but keep on continuously pushing towards it, and then reach that stage where like rejections are okay, failures are all fine. It's just like you're waiting till the day where things start to change, and then you go back to the same story again.
Good. So like you have a new lab in the making. You have a moonshot idea. Now you are in discussion with your supervisor about the topic. So you zero down to this particular thing as one of your thesis studies this particular paper. But if we see in your thesis, you very much concentrate on the topic like bridging the invasiveness precision gap. So if you could elaborate this a bit, like what is this and how does it translates to the study? And I mean,
Yeah.
is it very specific to
No.
the niche or is it
No. No. No.
genuine
Yeah.
general problem that you are planning to solve? And one of the solution is this paper, whatever is trying
Yeah.
to do.
Yeah. No. Fair enough. I'm like, this is like the one of those fundamental limits we see. I'm like, I think how should I put it? So the thing is, I'm like, there are like a lot of, I'm like, in general, if you look into the world, there are always like, I'm like blanking out on a few specific examples,
Yeah.
but I think one of them is frequency bandwidth. That's it's a constant. So it's always uh like tussle between whether you want higher bandwidth or like say I think it's probably frequency bandwidth. I don't remember exactly. So another thing is there are so many trade-offs. I'm like there are fundamental constants around it where I'm like you have a product of two things and which is a constant. So that's the same kind of a trade-off we see when it comes to invasiveness and the precision. And like, so the thing is, I'm like in general, these are all empirical like relations we find in our day-to-day life, in whatever kind of I'm like not just about research but everything. I'm like Moore's law. That's another kind of a trade-off, right? And so wherever it comes to, there is always a trade-off between two things. And when it came to like the neuromodulation, and that's the first trade-off I see. And then that's where I'm like, okay, how do we bridge this, or how do we overcome this kind of a fundamental trade-off? I'm like, to just give you more idea about neuromodulation technologies in general, I'm like, there are something called non-invasive technologies, which involves say TMS, like say I think it's like transcranial magnetic stimulation, and there is something called TES, which is transcranial electrical stimulation. There's something called TFUS, which is transcranial focused ultrasound stimulation. So this, when I say all of this, there's a constant of something called transcranial, which is you do not want to, I mean, you are trying to modulate the brain from outside the skull. So you are not like you're not doing the invasiveness into this at all. So you're trying to be non-invasive and then being outside the head and then trying to modulate the brain. Now the thing is, this is the limit on the invasiveness where you are not touching the skull or you're not going inside the skull at all. So, but the thing is, when you are at this limit of being really like non-invasive, the precision which is associated with these technologies is really bad. I mean, you're talking about millimeters to centimeter scale modulation of brains. I'm like a single neuron is 10 micrometer, like that's the soma size. So I'm like, when we know a lot of these neurons, I'm like, there are some neural circuits which will be like maybe hundreds of micrometers in like the cubic volume or something like that. So you need to modulate those specific circuits to have some therapeutic effects. But the resolution you get with this transcranial approach is on millimeter or like sub-millimeter scale, so it just does not work. And like, people have been using this for decades. So that's where I'm like, these are the limits on the like the what do you call it, like say the invasiveness and the precision on this kind of modalities. On the other hand, we have something called these deep brain stimulation electrodes, where you can implant to a surgical implant, open up the skull, inject these electrodes inside the brain. You can really pinpoint using maybe even MRI or fMRI, find out which is the disease stage, and then you can modulate those specific circuits. It is tremendous. I'm like, these are FDA approved technologies. There's so much, like say, data which is there, which shows the kind of therapeutic benefits you can get from these BPS electrodes. It's immense. But the problem is, you're doing a surgery, you are inside the head, and then you are drilling holes. It can have like device failure, surgical risk, like infection risk. Then there is like a lot of people cannot go through the surgery. So it has its own invasiveness associated drawbacks. So that's the other extreme of it, where I'm like, you can get the precision, but it comes at the like like what's the word? Like it comes like on the other side you have a
It
lot
has
of
the own cost of
exactly, yeah, I'm like cost is a nice word. Yeah, like it comes with this cost of invasiveness. So the idea was always about, I'm like, can we find something which can have the precision of these electrodes, or and in not like say the invasiveness of the transcranial method. So that's where we're taking a really fundamentally a different approach to come up with something like circulatronics, where we do not do any surgeries, but we still achieve a resolution which is really, really like high. So I'm like, that's the kind of things. It takes a lot of non-trivial thinking to reach that stage. But I'm like, it was interesting to like do or build something like this.
I mean, tell me if I am wrong. Like in a very
Mhm.
broader aspect, like invasiveness precision gap is your philosophical problem that you want to solve, and one of the application is the paper that has come out of it. Is that a way
Yes,
to put?
I'm like, yes, I'm like that's one way to put it for sure. And the thing is, I'm like as a I'm like now I can call myself as like a neurotechnologist. So and the thing is when I look at technologies in general or like what is needed in the field, it's always I'm like I'm looking at what are the fundamental problems which exist there, and then how do you come up with an alternate way which can bypass these fundamental limitations? And then I'm like, neuromodulation, of course, that's just one part of the work. I'm like, I'm like, I have my like many more big ideas I want to tackle or like explore. But when it came to neuromodulation, this invasiveness precision was the first bottleneck which shows up. That's where I'm like we developed this kind of a technology. And then of course I'm like within neuromodulation, like we show a platform technology where I'm like this concept of targeting neuroinflammation we demonstrate, but now the big task now is to apply it for specific diseases, be it Alzheimer's, be it glioblastomas, be it neuropathic pain. So there's a wide array of diseases where we need to validate this technology or this concept and then see what kind of therapeutic benefits we will achieve using this kind of an idea. So I'm like, that's the one program around it. But then the thing is, I'm like, don't need to limit yourself to neuromodulation, right? I mean, there can be many other technologies or like many other like big challenges out there to explore. So it's just like I'm at the moment exploring, figuring it out. What are the next big problems to solve, or like what can be the other things to explore as well. And then yeah, I'm like, what can be just working on this is also pretty much fine as well because you come up with a treatment for one specific disease. That's a big deal in itself.
Got it, got it. For the
Mhm,
sake of, normal laymen like us, like we who are not too much known to these new technology or the, terms. Like when we hear the word like brain implant, we only see the open skull and there is a surgery going on. So, to explain it to a normal person, like what is the fundamentally different approach that this
mhm,
circulatronics, you the term you are using,
mhm.
is different from a
Yeah. Mhm,
implanted
mhm.
electrode. So if you can
Uh-huh.
elaborate.
Yes, yeah, yeah, no, fair enough. And the thing is, like, let's define brain surgeries or brain implants first. The thing is, it's like there are two kinds of technologies. And like when it comes to brain implant, one of them is about this brain computer interface. And like Neuralink is a classic example of it, what it's doing. So I'm like, there they are trying to record from the like say neurons and then understand the neural pattern and then see can we like use our brain activity to do certain tasks. And that's the idea around PCS. But I'm like, what we are focusing is about more about therapeutics or early disease detection. So when it comes to therapeutics, it's always like say, I'm like there are certain brain regions which are responsible for a given disease, which might be let's say neurodegenerative diseases, can be an example where like you may have a plaque accumulation in epilepsy, you may have some neural circuits which are hyperexcited. So what people do in these things, I mean, it's been really well validated. Where if you can implant some like you can implant let's say electronics or electrodes, for example, in those regions, and then suppress their neural activity, then you will have therapeutic benefits out of it to do. This is just one way of doing it. The other ways can be you can take drugs, but then the problems with drugs is you will have systemic side effects as well, which people do not want, and like it can be really harmful as well. So that's where you are not like prescribed those drugs or other methods either. And then sometimes in many cases there are no alternatives. All you can do is just an electrode which can electrically modulate or like say the neural activity in those regions and then can have it will have therapeutic effect. So this is how things are done in general. But to implant anything, you just really, I'm like, it's like if you have to, like say, access the veins in a body, if you have to do an injection, you have to do an injection. I'm like, there's no way to collect blood otherwise unless you poke a needle, collect the blood, take it out. So, and then if you want to inject drugs, you will have to do the same way as well. So the thing is, that's the way with brain. I'm like, if you have to inject something into the brain, the only reason so far was okay, if you have to inject something, you have a skull sitting there, so you cannot directly inject. So you need to now create a hole in the skull and then inject. And then in cases like these therapeutics, it's not like needle injections where you inject and then you take it out. You have to let things stay there, and then you will have to live with it forever. So that's the kind of typically how brain treatments have been. But when it comes to, let's say, circulatronics, we do not need to do this anyway because there's an alternative to implanting electronics in the same region. It takes a different path. And that's so it's just like instead of going through the skull, opening up, doing a surgery and doing it, we're like, okay, let's just not do that way. We keep it as it is. We'll inject things the way we have been doing other drugs, or like when you, let's say, do some blood work. And then we're just injecting into the bloodstream. And now the electronics will self-navigate, reach the same target regions in a completely autonomous way. And like you do not have to look at it, direct it at all. It will reach on its own, and it will get implanted in the same exact place. And now there is no surgery involved. And like the pain is almost not there. It's completely minimally invasive, not surgery. And now you can start modulating the same neural circuits, which previously would have taken you so many, like say, like so many surgical interventions and the risks which are associated with it. So it's just a different way of looking at it. I'm like, it's like you can eat. I'm like, I'm like, it's not a nice analogy where I'm like, you're like, if you have to eat food, you can just eat with a spoon or with your fingers. Sometimes if you do not have, I'm like, if you have some other options, and you can take it as a fluid as well. So I'm like, I'm like, the idea about food is you want energy. Getting energy can be many ways. So it's just an alternative way, but if it's really safe and if it's something which is of use to the patients, then I'm like, that's the way to go about as a society, or as like maybe like say doctors. So it's just like we're creating a new, different alternative which was just not there, and then no one had even thought about going from this perspective.
Got it, got it. I mean, if I'm trying to, to say in the analogy, like we are not doing any cutting of a skull to do anything, or we are not doing any laser. We are just as if we are taking a vaccine, just injection, and it will
It's like
that is where we are coming to, like
yes,
the term you have used in your paper, that is the SWEDs. So this cell electronic hybrid, this goes into your bloodstream and it will do the work as if we are using some kind of a medicine that we do via injection. So here I want to understand, like can you give me a journey, like once you have injected a SWED or this cell electronic hybrid
mhm,
until it
mhm,
reaches its destination and start doing the, like what happens in a very, I mean, very
mhm.
layman
Yes.
term.
Yeah. No, no, no. Sounds fair. Yeah. So the thing is, I'm like, when we inject these, like, so the thing is, sweats is basically the electronics. I'm like, we define it as it's a subcellular wireless electronic device. So the electronics is the sweats. We create something called a cell device hybrid. So, or you can call it a cell sweat hybrid as
Yeah.
well, because that's the electronics of the sweat here. So it's the hybrid which we inject into the vasculature. Now the thing is, once we inject it into the vasculature, I'm like, we inject it into the veins. So I'm like, the blood is continuously flowing. So these sweats, like these hybrids, are continuously, like say, just circulating throughout, like the vasculature. I'm like, that's the first thing they do. Okay. Internet is still there.
Yeah, it
Hello.
dropped for a moment, now it's up.
I see. I see. Okay. No, sounds good. So the thing is, I'm like, these hybrids, they're continuously circulating inside the vasculature. So that's why we call it circulatronics, because it's the
Okay.
is the electronics which is circulating within our body, in the vasculature. So that's where we define it. We call it circulatronics. So it's just continuously circulating. And now the thing is, let's say you have an inflammation or you have a like some disease which is causing inflammation. Now the thing is, which is really unique to like, well, not unique, I mean, which is really fundamental to any inflammation, is that the body reacts to it. And the thing is, let's say if there is an inflammation in the brain, you have neurons, you have glia cells, you have astrocytes. And these are the three major population of cells. So the glia cells are the immune cells in the brain. So once they detect that there is inflammation there, they start releasing certain chemicals. And like a few of them to name, and like it becomes too technical, but let's say TNF alpha, IL-1 beta, IL-6, some of them. So these are some, just imagine some chemicals which are being released just because there is inflammation. And the goal of these chemicals, why they're being released, is like glia cells understand that okay, now there is inflammation, it's trying to repair it, but in case it cannot do it, it wants to recruit some external cells to help it. So like when you want help from outside cells, and like the immune cells are the first responder, and like you are recruiting basically immune cells to help suppress down the inflammation in the target region. And now when these chemicals, the way they work is, I'm like, it's a classic diffusion system. So where I'm like, there's a higher concentration of these chemicals at the inflammation site, and then it starts to diffuse out into the blood vessels at different, in the vasculature. The further away it is, the lower the concentration is, the closer you reach, the higher the concentration is. So it's like you're creating a gradient of these chemicals. With immune cells, especially monocytes, they have a really well-defined process to react to this, and there's something called chemotaxis, which is like with this process, what they do is whenever they detect these chemicals in the vasculature, they start to get attracted towards the higher concentration of these chemicals. So let's say I'm like, if this is the inflammation site, the diffusion of the chemicals will go from somewhere here or in all directions. And the moment while the circulatronic, all the hybrids are rotating or like they are circulating in the vasculature, the moment they detect even a trace amount of this chemical in the vasculature, they get activated. And then because of this chemotaxis process, they're trying to go towards the, like they're following the gradient so that they can reach the core of it. And in the process, there is something called blood-brain barrier. And like, if the inflammation is in the brain, if it's not in the brain, there is no barrier. But unlike, that's one of the strictest, stringent barriers which exist in the body. But that's the beauty of immune cells, specifically monocytes, that they can cross the barrier very easily. But if you just put up, let's say, SWED or an electronic device, it will never cross. And like even like hundreds, like even if you have nanoparticles, the hundreds of nanometer, well, maybe not hundred, I'm like maybe let's say hundreds of nanometer big, they cannot cross the barrier either. So it's like virtually impossible to cross. But because the immune cell is following this chemotaxis process, and the cell is carrying the device with it, it crosses the blood-brain barrier and then reaches the target region. And then this way, we can have a hybrid which is just randomly circulating in the blood vessels. Now it has reached the target, and now with external transcranial light, you can activate the device, which in turn will start modulating the neural activity. So I'm like, this is how the general mechanism or the life of a hybrid inside the body looks like.
Got it, got it. So, just wanted to have some clarification, follow up. Like when you say cell electronic hybrid, the cell is from the patient. Like here, you use mice for the. It is the same mice cell that you have to use for making the hybrid, or it can be different.
No, so yeah, so in this specific work, we used a standard cell line, but
Okay.
we tested it out with like the mice own cells. And like we derived something called like the bone marrow cells.
Okay.
And then you can make monocytes from the bone marrow and then use those cells as well. So the the idea is that you can take the mice's or the human's own cells and create these hybrids and inject them back. I'm like, it's something similar how dialysis works, right? Where you can like collect the cells, like the cells you do not want, you can
Hmm.
take them out. Like I think there's some process called electrophoresis. I'm blanking out on the name,
That's
but
fine.
you can always collect the cells, create the hybrids, put them back into the same patient so that they are innate, there are no immune reaction or anything which will happen, and then we will have a better like performance.
Good. Good. And another thing is like there are many kind of white blood cells. You chose monocytes, as you said earlier, that the only purpose like to invade into the part that when the choice of monocytes, how do you zero down to
Yes.
monocytes?
Yeah.
I mean, there are
Yeah.
many
No. So the
types.
thing is, I'm like, yes. I'm like, yeah. So with monocyte, there are two really good properties of monocyte. One of them is they are the first respondents when it comes to neuroinflammation. From like, of course, we have different kind of cells. I'm like, say, from monocytes, macrophages, T cells, B cells. I don't know. There's so many. And then even within monocytes, you have different classes of it. And like macrophages, you have different versions of it. But that's the thing where monocytes are really the first respondents within the immune cell. And then the other nice thing about monocytes is they actually cross the blood-brain barrier in a really efficient way. So because we were creating like we are targeting neuroinflammation, wanted to make sure the cell we are choosing, like say, fits in both the criteria of like say, okay, they should be the first which gets recruited, and as well as they should cross the barrier. Because if they don't, then there's no point. I mean, you'll never have the electronic inside the tissue. So that's where I'm like, these were the two reasons, and then the monocytes were the first one which really ticks it really well.
So I mean, if we go by
Mhm.
that, like, so there are two questions that come in my mind. One is like, I mean, first of all, like these particular switch, these are anyway, it's an electronic device. Like how it is getting the power from. So that is something you also might have faced, like, and you have addressed it into your paper. I mean, if you can elaborate the power part, and the second part is once the job gets done then
Mhm.
the sweats, those are microplastics, they need to come out, like what happens there. So if you can elaborate in these
Mhm.
two parts, it will be helpful.
Yeah. Yes. No, no, fair enough. Yeah. So the thing is, the first thing is the electronics. I mean, we use photovoltaic devices. So the thing is, when it comes to when it comes to photovoltaic devices, we optimize the device to perform at NIR light. So it's like say, around 800 nanometer, which is known to penetrate really deep into the tissue. So that's where we use. I'm like, we knew. I'm like, if you want to power these devices, you need to do something which is like transcranial, so that the light we are using it should come from outside the skull. That's where I'm like, you went for NIR light, which can penetrate really deep into the tissue and then activate the devices. So that's where the device part is. So now the next thing is once the job is done, there are two approaches to it. So the first thing is you can have the microplastics, but you can have microplastic which is degradable as well. So that's the part where I'm like, the thing is, I'm like, in this specific work, we have focused on the biocompatibility that even if it is placed there, it does not have, it does not harm the cells or the tissue in any form. That's why we went for the organic polymers, which are supposed to be highly biocompatible in this. And then unlike the other materials we use, and one of them is titanium nitride. These are like which are like metals which are used in like say even like the bone implant. I'm like in the legs. So I'm like these are materials which are highly biocompatible, and the body like does not have any immunoreaction to it or toxicity to it. So in this work, we show the biocompatibility. In the follow-up, we can replace the microplastic, which can be degradable over time, so that things just degrade right there in a biocompatible way. And like that's why we call it biodegradable. And like once you have something like this, then things do not agree. And then I'm like, just to give you some numbers, a single device weighs around 25 picograms. So the mass which is associated with it is so small that I'm like once it degrades, it just in a layman's term, it's like it just vanishes right there. Yeah. So
So I mean, from the
mhm,
battery aspect, so you are basically using the light from outside to wirelessly charge the device till it's getting worked up. Is that
mm,
very
no. So the way, like, so the thing is, okay, photovoltaic device, like, think like the way typical solar cells work
okay?
is like you turn on the light, it starts generating energy right away.
Right,
So it's I'm like it happens on microsecond scale.
right, right.
So when it comes to the devices, you turn on the light, the devices are activated right away. And then you turn off the light, the devices shuts down right away. So it's like there's no battery or no charging or discharging associated
Okay.
from that point.
I mean, you remind me of that
Yeah.
Koi Mil Gaya movie, Jadoo needed dhoop for the energy parts of.
Well, yeah, I'm like, well, it gets charged. I'm
Yeah,
like, we don't charge it. So
yeah.
I'm like,
It's
that's probably
activated
one that,
at the moment. There is no charging delay or latency here. Okay.
oh, is it? Yeah. Fair enough. I'm like, with Java, I'm like, it holds on to the energy for a while. It runs
Yeah,
for
yeah.
some reason. Yeah.
True,
Yeah.
true. Yeah, yeah. That's a good thing to know.
Mhm.
So now, like, I mean, if we move to, I mean, we discuss mostly the technical parts, whatever is required. So we will
Mhm.
move to the other section, like the eureka moments and the experimental challenges.
Mhm.
We will move on.
Yeah.
So I mean, this project is very ambitious. I mean, right now it is in mice. You are all in the process of a patent. Our Dr.
Mhm.
Sarkar is also building a startup, has already spun up a startup, Kahiya Technologies, I assume. Like
Yes.
I mean, there are usually a few this might actually work moments. Like, I mean, what
Mhm.
was the moment that you found in your lab or in discussion with your supervisor or your co-authors
Mhm.
or while doing experiment? Like,
Mhm.
when you understood, yeah, nah, this is something gonna be big. I mean, this is not some failed
Mhm.
experiment. I mean, what was the moment, or it was multiple trial and errors and then you came to it? Like, what was the journey about?
I'm like, no, I'm like, the thing is, it's always, I'm like, when you zoom in, I'm like, there are two ways to look at it. I'm like, when you really zoom in on a day to day, you do not get any eureka moments ever. I'm like, it's a continuous thing where I'm like, things don't work. Something which looks like might be working takes a few more iterations when it like you feel like more confident. Okay, this thing is working or like reaching there. But when you zoom it out, I'm like, then I can say that there are like a few instances. I'm like, one of them was like the device characterization because I'm like, once we got the really high efficiencies on the devices, that was like one of those that probably a week or something where we were like, okay, the devices are performing better than what we had like initially planned for because I'm like it was all a numbers game for us at the end of the day. So like okay, we need to hit these numbers. If these numbers we get from the devices, from the implantation, from the neuromodulation, if we get hit these numbers, then this technology will work. So it was from that perspective, the day we characterized the devices with numbers which were way better than what are like say the threshold was. I'm like, okay, if anything goes below this, it doesn't work. Or like we'll need to spend maybe months and years more on optimizing this. So the same thing happened for in vitro things where I'm like, okay, so creating the hybrids, how stable they are. Can they function as intended? And then we did some transmigration assays to show that the functionality of the hybrids is still intact. Like just not just because cells will transmigrate, but whether the hybrids will not do or not, we did not know. So getting those data sets some days when I'm like, yeah, like okay, and then I'm like, yeah, all these experiments just takes days, sometimes weeks. So it was just like that kind of a thing. But these were certain milestones where we are like, okay, this thing works, this thing still functions, and then we first saw some neuromodulation results, and those were like probably the three big days or like moments where like okay this technology will work, it's just a matter of time rather than like whether it will still work. I mean that's the other part of it where I'm like when you work on it you're always pivoting, you're always optimizing till you make it work. So it's just like getting that the first confidence, okay, this can actually work. I'm like was few of these moments which made it that way.
I mean, if we approach this from the other side,
Mhm.
like, I mean, there are many moving parts in your experiment. Like, one was, first of all, when I go through the paper at the last, after the names, then there is the section where it start where you did the fabrication part and all the things, like you did fabrication, the attachment, like the blood vessel part, the neuromodel. These are very different kind and different way. So my question here is like, among them, which was like, what was the bottleneck of all the moving parts? Did you find where you got stuck for many days or many months, or all of them were of equal complexity, like?
No, I think there were two things which really highlighted for us. And the one of them was, of course, the first implantation results, like the self-implantation results, to get really good, like say, self-implantation of hybrids at the target site. That was the first thing because it took a lot of trials and errors and optimization in the protocols to reach that stage that okay, this thing looks good. And then of course, I'm like, we can still keep on optimizing. I'm like, we have much better protocols now, but I'm like getting that. And the other thing was validation of neuromodulation results through electrophysiology. That took us almost, I don't know, maybe 7 or 8 months of continuous experimentation to collect, like to just, I mean, we had to literally build the entire ETH Zurich to collect the data and then do everything right to get those first initial results. So I'm like, that was really difficult. I'm like, these were like the things which I'm like, yeah, took almost like that was majority of the time. Where I'm like, maybe a year and a half was just about these two things. But yeah, I'm like, everything has its own journey, but I'm like, these were just like something I feel like more relieved after doing experiments than anything. But like, okay, now this is done. Now I can move to the next thing. So yeah.
Yeah. So obviously, your team and you will be going for the human trials in subsequent iteration. But I mean, what I want to know from your is like, what is the vision for this particular application? Like, what will be your 2.0 or the 3.0? What are you imagining, or what kind of particular diseases or things you want to solve first using this non-invasive
Yeah,
surgical part? So can you elaborate on
yeah.
that?
No, yeah, I'm like at the moment I think Deblina is focusing more on this disease of neuropathic pain
Okay.
because I'm like it's one of the, like say, the immediate things we see. It can have a really good impact. So that's where I'm like, we are really targeting neuropathic pain at the moment. And then I'm like, there will be like say Alzheimer's is one, and then probably a few more diseases to follow can be the, like say, the second and the third, like say, focuses of the probably the lab or the startup. But I'm like at the moment it's, I'm like, and then of course there are a lot of iteration and things need to be done to take it to human trials, or like say, like like a lot of technological, like say, robustness we need to add into this.
Got it. Got it. So, like,
Mhm.
it's safe to say that right now you are a freshly minted PhD. So, what are
Yes.
your plans right now? Like, you want to go for the startup route, or you want to go for the more postdoc route and the academic route, or any plan with this particular product to carry on, or you will leave it to the labs? I mean,
No, I'm like, well, I'm like, I already started to work on it. So I'm like, I already joined this Institute of Neuroinformatics in
okay,
Zurich. There's like a university and ETH Zurich affiliation. So I'm like, and for my personal reasons, I wanted to be in Switzerland, in Zurich as well. So things turned out to be nice. So that's where I'm already made the move. And then I'm like, at the moment, I'm like, that's something which I'm like, it's just like, I'm like, when it comes to like working in a different country and all those things, it's not easy to continue the same thing in the same,
right.
like, say, active way. So that's where I'm like, I'm also interested in other technologies. I'm like developing some other kind of technologies at the moment, and then we'll see how things go. But yeah, I'm like, at the moment, hopefully, maybe some academic jobs at some, I'm like, maybe in a year or two. So that's the kind of way I'm looking at it. But then I'm like, you never know. The plans always change, things
Right, right.
always happen. So yeah.
And I mean, we are almost right to the fag end of our interview. Like, just want some, I mean, questions regarding this. Like when you were working on these devices, I mean, and that enters the brain and change its activity. I mean, from the philosophical perspective, how does that affect your own intuition, like of myself or mind? I mean, in the sense, I want to don't want to sound very metaphysical, but are there any effects like hallucinogenic effects of this or a side effect of this that might alter a life of a particular patient? Is there something like there is any
No,
dark side of this
uh,
invention?
no, fair enough. So the thing is, I'm like, this is something which probably a neuroscientist might give you better answer. And like, I can just give you one. And like, when you talk about say hallucinations, for example, I'm like, hallucinations in some form are a form of memory built up or a memory recall, something like that. So the thing is, I'm like, there are certain neurons on the something called engrams, which are responsible for doing something like this. So the thing is, I'm like, if you want to like have these side effects, so I'm like, the thing is, there are always some specialized cells, circuits, which are responsible for it. So the thing is, I'm like, if for some reason, I'm like, I don't think whether this thing is true at the moment, where I'm like, when you have some diseases, when you're targeting, say, for example, neuroinflammation, I'm like, when it comes to, let's say, I'm like Parkinson's, for example, and we know subthalamic nuclei is the target. When it comes to neuropathic pain, there is like, say, there are neurons which are in the spinal cord, and I think these are some DRG neurons which are responsible for them. So the thing is, we are targeting those brain circuits or those target regions. So when we do that kind of a thing, whether those are responsible for like, are those circuits also involved in some other functions? So that becomes that kind of a question, right? So the thing is, if you have maybe Alzheimer's is a good example for it probably, where I'm like, okay, if there are some like the engram cells, if the inflammation is associated there, and then for some reason, and that's the other part of it, when you have to do a memory recall, you have to make a lot of the neurons or all the circuits engram cells associated with the memory fire simultaneously, then only the memory recall happens. So I'm like, when I talk about probabilities, the numbers will be really low. So I don't think anything like that will happen. But in a off case, in a rare case, because we never know, because I'm like, the brain is just so complex, the neurons by themselves are so complex that it may do something like that, which might be possible, but we'll always have a reason or an answer for it. And then I'm like, once you understand the reason behind it, you can always come up with a way to mitigate it. Because it's like, if we can do something like this, we can always find some other solutions for like side effects or like something else which is not intended. So I feel like if we understand what we are doing, then of course we can come up with a way to not have that go through or happen. But if we don't know, which honestly is true at the moment, where I'm like, a lot of things we are still trying to understand and then see how different neurons work, different brain circuits function, how they are connected across different regions. So it's a lot of understanding which is going on at the moment. So I'm like, we may not be surprised if we find something which is not the desired effect, but then we'll start. I'm like, as researchers, that's our job, right? And like, if something you observe which is not expected, then you start looking into it, that why exactly it's happening. And then we figure it out, and we'll figure it out. I'm like, hopefully not us, someone else. And the people are always curious, smarter than us. They'll always find out the right reasons. So it's just a thing. I feel like I'm like, yeah, the odds are really low, but if something like happens, you can always find the reasons or work towards it.
True, true. I mean,
Mhm.
now if we come to the, I mean, paper part. I mean, I see two problem. It's a selfish question. Also, I too want to understand this correct, because there are two giant things that you have done. First of all, this is a nature paper, Nature Biotechnology paper. You are first author of it, and it has multiple co-authors you have, and they are all from different varied background that was needed for this particular project. Now, number one, like, first of all, I want to know, like, how did you make this coordination done apart from supervisor's help? How did you coordinate to write a coherent paper, number one? And number two, was Nature Biotechnology the first I mean natural choice for you, or you also pitched it before to other journal outlets also, and then if there is any rejection, then finally you got a home in Nature Bio? So can you, if you have this collaboration part
Yeah,
and the paper journey, it will be helpful
yeah.
for many of
No,
us.
no, no. And the thing is, I'm like, when we started working on this, and the thing is, the path towards working with this kind of work was, you start with electronics first, you make it work, you make it functionize, then you go to the in vitro part where you make things work there as well. Then you go to the neuromodulation side, and then you make things work there. So the thing is, I'm like, the path was pretty much well defined, and everything takes time. I'm like, it was like we're talking about years and years. It's like we can do some things in parallel, but it was really all over the place. So the thing is, I'm like, when we started, it was like, okay, I was always, I'm like, I can say, I'm like, I was fairly confident about the electronics, but I'm like, this should be doable. I'm like, I do probably won't need a lot of external help or people supporting me. But when it comes to other things, I'm like, there's a lot of learning for me, as well as sometimes the complexity of the experiments were too huge. I'm like, it's like doing the entire experiment. I'm like, when I used to do these experiments, it used to take like, say, from morning to late night, and then you're just continuously doing things. You're like, you barely even get time to just have food or something like that. It was really long, insanely long experiments with a lot of moving parts. So it was like you realize you cannot do some experiment just by yourself. So you need support. So that's where I'm like, we started to hire the right people. So like, okay, we are like maybe a year from now, we probably reach that stage where we need a chemist, for example. So let's start looking into the process. If we can collaborate with someone, if someone is not there, let's just get someone in the group. So like who will be a chemist? Like when it comes to neuroscientists, I'm like, we need a neuroscientist when it comes to neuromodulation. Those things. So like, okay, let's start getting making connections, making contact, and getting the people. So it was always done keeping the big picture in mind, looking at what stage we are at, so that we can find the like right support at the right time. Because sometimes, like, if you hire someone maybe a year ago, or you like collaborate with someone saying, okay, I'll reach there in 2 years. I'm like, who knows what happens in 2 years? I'm like, technically COVID happened when I joined. So like, who had been COVID will happen. So those things are always there, but it's like planning and then doing things, predicting in a nice way. So I'm like, those things were part and parcel of it. But that's where I'm like, all the collaborations and everything happens. Where we're like, okay, we need someone with this specialty at this part of this at this stage of the project. So let's just like initiate those collaborations, hire those people, and then work with them. So it was that kind of approach. And then the other thing you mentioned,
The journey of the paper. Basically, I wanted to know, like,
oh
what
yes,
was the R&R
yeah,
journey of this one? How many R&R had to go through it?
no,
And
yeah, no,
the main thing is, like, was there any particular review comment that had to take you back again to the lab, or were the review comments
oh,
loosen enough?
yeah, no. I'm like, this was tough. I mean, it took us almost more than 2 years or close to 2 years to get it accepted or
Okay.
like published. I'm like, the thing is, Nature Biotech was nice. I'm like, the editors were nice, really like the idea and everything. But then I'm like the reviewers had their own
Hmm.
questions
Yes.
or like concerns as well. So I'm like, the first revision took us, I don't know, maybe 8 or 9 months,
Okay.
and the second one took us again 8 or 9 months. I'm like, they had a lot of questions, and they were like really good, constructive questions. I feel like I'm like, it doesn't sound nice, but I'm like, the reviews were really nice to us for sure. It just like the questions were valid, and some of the experiments were too difficult probably for my expertise. So it just took time to learn to get the expertise in and then collect the data. So it was just like a nice, tiring, like really difficult process of review.
How was
But
reviewer two?
well, I'm like in my case,
Uh,
it was reviewer one.
okay, so reviewer
Reviewer two
one.
was
It can be the any reviewer.
yeah, yeah. Yeah. Well, yeah, I'm like the thing is, it's always one reviewer, so it's always that person,
Right.
right? So yeah, so I'm like, there was like one reviewer was tough. They had really good questions. It took us a lot of time to come up with sometimes clever experiments, sometimes brute force, sometimes probably luck. I don't know, or sometimes like a lot of help and support from a lot of people. But we were able to go through this. So I'm like, yeah, it got through, which was nice. Like, we did not go into the third round as such, which was nice. Really happy about that. Otherwise, it would have taken I don't know how many more months.
So
But
and
it's good.
yeah. So
Mm.
final only two questions. Number one is
Okay.
standing right now in your position, a
Mhm.
person who is want to switch from industry to academia, or want to a
Mhm.
student who want to join a PhD or has just joined PhD. What will be
Mhm.
your single advice or I mean experience, whatever you want to say it, that is one.
Yeah.
And number two question is like, what are you currently reading, any book or something, or any book you want our audience to follow, like this
Mhm.
book changed my life, or this books is
Huh.
something that
Okay.
stick to me, I go back to that book. So
No, then I see. I see. Interesting. Yeah. Okay, so let's do the first one first. So, unless when it comes to forgot.
yeah, I mean, who has just want to join
Okay.
the
Yeah.
PhD
Yeah. No,
path.
no, no. I remember. Yeah. I think one of the things I'm going to say, I'm like, it's just about two things. One is the advisor or the group you're joining, and the other thing is just be open to meetings. Because I'm like, I thought I was a bit rigid initially, where I'm like, I want to do maybe focus on one aspect of the work or something like this rather than the other thing. But then once you're less rigid about it, you get to learn a lot. And it sometimes becomes nice. I mean, you may like more interesting things. I'm like, it could be like, okay, like, I'm like, you maybe, let's say, you may like the new field you want to work in rather than your core training in whatever field it was. So, I'm like, just like being open to learning new things and exploring. And the other thing is more about like what kind of a group you're in, because I'm like that matters. I'm like the people matters a lot because you will be interacting with them day to day. Science is always boring, depressing at the end of the day, but it's the people who make it nice and more fun and more interesting. So as long as you get along well with people and you like what you are doing, you learn more things, you will find it interesting, and then you'll go through. But otherwise, I'm like, yeah, it's not easy. But yeah, I'm like, when it comes to books, I'm like, I feel like I don't think anything else comes to my mind which would say like it really changed my life. But I'm like, I read a lot of non-fiction. I'm like, especially around like the books. I'm like, I'm like, especially around like the things which were like happening in the med tech or like technology field. I'm like, I think there were like a few of these biographies which I read about scientists. It was nice. So I'm like, those kind of things are good to just see the different aspect of the side as well. Where you're not just looking at like the work, but it's also about the humans behind it. So those kind of things I like. And then I'm like, sometimes I flip completely to non to fictions as well. So I'm like, why not? I'm like, you do get some crazy ideas from some fiction you might be reading. So that's the other part of it. So it's just like
I mean, if
no
I
hard and fast.
rephrase this question in another way, like you are given a choice, like whatever book you have read from school days to now, you have to choose only one book, and that is something you have to keep for the rest of your life. If this is the question, like which book you will choose and keep it for the rest of for.
I think the most recent one which I can think of, which I really liked, and I don't know whether I'll find anything which is I want to keep again, but the most recent one I read was this book called Code Breakers,
Oh,
which was pretty nice. I'm like, it's about CRISPR technology and like the how things behind it ran in the system. I'm like how like what kind of like people were involved, what kind of like say the dynamics of academia in general was there leading up to the technology. So it was a nice read. Like it gives a good idea of how academia can work in general when it comes to sometimes really high impact technology. So it was nice.
Okay. I mean, that wraps up our discussion for today. I mean, you gave a lot of time to me, and I mean, you took time and answered the query. It was really
It was nice.
enjoyable.